Hello, welcome to the second RustShort, short video about Rust safety. We're not going to focus on the syntactic details of how you make your programs, how you construct your programs to be safe. We're going to focus on a thought experiment about how Rust safety analysis works. So there's a lot of material above this region that we're looking at, on this page toward the top, that explains some of the terms we're going to use. And if you open this URL, you'll be taken to this page, and you can check out all that material. So for now, we're just going to proceed with this thought experiment, trying to understand how Rust safety analysis works. So I have this hand-drawn sketch, and this we're supposing that we can map all code from our any conceivable Rust program into the XY plane, and we've shown one lane of that. So here's some code, and this boundary is a soundness boundary. Anything upstream, any code upstream of this boundary is unsound. Any code downstream of this boundary is sound. Now, this boundary purports to represent the exact place where code, changes from sound to unsound. Now, that's not computable. No real process can evaluate that boundary, and that's what we're talking about. So, by the way, this vertical axis represents the amount of effort to compute whether you lie downstream or upstream of this boundary. So the closer we get to the boundary, the more computationally intensive it gets to be. And this spike to infinity is trying to illustrate that it really isn't computable. There's places where things we just can't determine in a finite amount of time. But given that, so anything that lies above this boundary is obviously unsound. Anything that lies below this boundary is sound. But a pragmatic compiler like RustC has to do its evaluations with something that's computable in a reasonable amount of time. So Rust has chosen to represent soundness by an invariant. Any sound program must not share mutability with references. So in other words, if I have a mutable reference to some piece of data, I can't have a reference of any kind, a second reference of any kind to that data. I can only have one mutable reference at a time. I can have as many immutable references as I want. But if there's a mutable reference, that's the only reference into that piece of data. Okay, so that's what the analysis of that invariant across your program is done statically at compile time. And because it's a simplification of this actual boundary, and we simplified it so that its expense was much lower, we could compute it in a very reasonable amount of time, it won't detect all safe programs. So anything downstream of this static analysis boundary is provably safe. Anything between, in this region 2, between the Rust analysis boundary and the soundness boundary is sound, but can't be proven to be so in a reasonable amount of time. And anything upstream is unsound. Okay, so, and this boundary is determined by the invariant that we talked about, the fact that we don't share mutability through references. Now, there's a little more to that story, and I'll come back in a couple of minutes to that. So what do we do? So here we are in this, our program may be in this, some of our program may occupy this region in area 2. And so the compiler will reject it, but it's actually sound because it doesn't go upstream of this soundness boundary. It turns out that a lot of the library types in Rust, especially the container types, fall into just that category. The things they want to do, that they need to do, are very useful, needed operations, but they require a relaxation of the invariant. So in a unsafe blocks, the compiler allows some fewer restrictions on the way references are handled. There are still some, but fewer restrictions of the way references are handled inside the unsafe block. And so the Rust team has designed these container classes, container types, so that their unsafe block allows them to still compile successfully, because what would have been rejected because we can't evaluate it is now being told by the unsafe block, ignore this. There's a weaker set of constraints you still have to meet, but you can ignore this hard, no shared mutability. That's really what they're trying to get around. And so and that works just fine. And so your program, if it uses these containers, vectors and vecdex and maps and so on, hash maps, your program is walking at some time through parts of this valley of sound, but we can't detect it, just because your program is not using any unsafe block. And so the compiler, when it compiles a standard library part, just skips over that, because of the unsafe block. And you don't have any unsafe blocks in your code. You're just using those types, and everything just works. And so a lot of your programs are silently walking into this, partially in this region. You don't know, you don't care. Okay, it just works correctly, and you satisfy the soundness guarantees. But there are other cases, perhaps what you want to do isn't quite covered by what the operations that those standard types provide. So there's a second alternative that is called interior mutability. And what interior mutability gets at is that you don't violate, at any point in time, you don't violate the shared mutability invariant. It's just that because of the way your program evolves in time, the compiler can't tell that you don't. So if that's the case in your program, you can use this interior mutability via this types called a ref cell and mutex and so on, do that for you. So they tell the compiler that they don't do any mutable operations. They lie to the compiler about through their interface. They say we're safe, but they will hand out references. But these are checked at runtime. These references are checked at runtime. And so what happens is that ref cell is sitting there with a count. So if it has any references at all and it gets a request for a mutable reference, it panics and terminates. Or if it has a mutable reference, it's operating fine, but now it gets a request for another reference of any kind, it panics, meaning the thread, it terminates the thread that it's on immediately without giving any access to memory you don't own and so on. So it's safe. That's used Most developers will use it very rarely. I think I've only used it once or twice in many thousand lines of code. You may well be, again, using it indirectly in the types you use. I've used the mutex a lot in my threaded programming, and mutex wraps a ref cell, and is doing this runtime checking of mutable references. Okay, there's a third way. So the first, the first way to resolve problems are to use the standard types liberally. The second way is to use interior mutability, but only as a last resort. You try not to. The third way is to change your design some way so that it no longer violates the shared mutability invariant. A typical way, for example, you want to build a graph class. So the graph classes are very hard to build if you try to link graph nodes with references. You get all kinds of problems with lifetimes and shared mutability. Very often a vector will need, a graph will need to share mutability. You may have two parents of a vertex, and each parent needs the ability to change the value of that vertex. So the solution to that is to use a vector, and you put the graph nodes into the vector, and then you establish the child-parent relations with indexes. So a node will contain an index for each of its children, and checking those references, traversing the graph is easily done by using that indexing. So that's a change to a design strategy. Instead of using references, we use indexes and pointed in vectors. And the indexes are always safe, because even if the vector is reallocated, the indexes are still valid, because they all refer to the beginning of wherever you are now, beginning of the memory that's allocated for that vector. So those three ways really cover the waterfront very nicely. Again, use the standard types liberally. Don't try to invent your own link data structures. Use the data structures provided by the library, or change your design a little bit so that it no longer violates the invariant, or as a last resort, use ref cell, or for threading all the time we use the equivalent of that. We use the mutex, because that's a runtime thing, and threads often need to share data, and so that's done with this interior mutability via a mutex. Okay, so we didn't talk about any of the syntactical things. How do I write code? That's safe. What are the constraints? We've talked about it a lot. As you look above here on this page, you'll see descriptions of all that, and the references will take you deeply into that material. So with that, we're going to bring this video to a close. I hope you've enjoyed the video. I hope that it helps you understand how safety is implemented in Rust programs, and it's a very sensible model. Makes a lot of sense, and it's not all that hard to deal with. If you don't understand the model, it can be quite daunting. But if you understand the model and how things, how Rust is really going about its business, it's not a big deal. Okay, so with that, I will say a fond farewell, and I hope I see you again in a upcoming video. Bye-bye.